Okay, thank you. So, hello everyone. Thank you for joining the RISC V Day Tokyo 2020. Uh, Today, I would like to present ASAMicros RISC V processor for ultra low power IoT and AI at the edge computing. So, this is about ASA Microsystems. We have started in early 2018. Our focus is on ultra low power and high performance IP for IoT and edge AI inferencing. So we have decades of experience on customer SoC development, starting from the customer requirements, then developing the RTL and going up to GDS2. And we have done in our team, we have lots of experience to develop the products in different dimensions. And since the RISC V is become an open source ISA, so we become interested to use this RISC V to develop the low power products for the customers. So this becomes motivate us to open up the ASA Microsystem INC. So here is the products that we are, or the target markets that we are planning to go for. So some segments like medicals, industrial robot, or building automations like this. So no need to say that the computation demands of these devices are booming. So for an example, in a smart camera or security camera, maybe 5 years ago or 10 years ago, people just like to record the CCTV videos, but nowadays they want to do the object detection and at the edge device, at the CC camera device itself should be able to detect the objects. Similarly, smart drones, it's no longer is just only controlled by some RC remote or something, but now it should have its own intelligence. So as a result, many edge devices are actually requiring their own computations from different perspective. But at the same time, these devices are mostly very power sensitive. I mean, we should have to give them sufficient computation at a lower power. So that's why the ASA's position is that we are trying to make a good balance of power and performance. This is very well known that power consumption goes up with performance, and it's a non-linear fashion. So current technology are not only relying on the processor, I mean for the computation, they are not relying on the processor, but also they are using accelerator blocks to meet the performance demand. On the other hand, we have our low power RISC-V processor, and we are going to deliver a low power vector processor as well to fulfill both demand. I mean the processor and also accelerators. So for the edge AI and smart IoT to realize the practical requirements of the products. This is about the RISC-V processors. So first of all, why RISC-V processor? We already know that RISC-V is an instruction set independent of processor architecture and implementation, and there are many not so many, there are several commercial RISC-V processors with their own microarchitecture for the same RISC instruction set, and majority RTLs are generated maybe chisels or from maybe they're using system Verilog or some high level language features. But on the ASA RISC-V, we have our proprietary, and we applied for the patent for the microarchitecture that implements the same RISC-V ISA in Verilog, and it is ultra efficient in gate count, die size, and power. Power low, die size is very small, and gate count is also very small. And this same code has a dynamic range of operating frequency. It can goes from 100 megahertz to gigahertz. You can achieve this performance in the same code. So this is the ASA RISC-V technology portfolio. Of course, we like to promote the RISC-V, and based on the RISC-V, we have processors for, of course, our low power processor IPs, and then we have the AI accelerators for the edge AI computations, and We also have a portfolio of SoC design, SoC peripherals like HV bus, XI bus, cross bus, SPI, CUART, very commonly used peripherals library. And we are also developing the vector processor for high performance computations at the edge. And we are also working for the multi-core. And we have also on our roadmap, we are planning to go for the chiplet where multiple cluster of the computation blocks can be connected on the die. And on top of that, any kinds of design, we need to have a simulator to simulate not the Verilog or just only the farmer we have written in C++, but this is a combined simulator that you can simulate your own ideas, your own SoC. So I will describe later about the simulator. And also the FPGA, because FPGA is also a main hardware driver, main semiconductor, becoming a major player in the semiconductor area. So nowadays, maybe many products that does not have covered the volume, in that case, they need the FPGA rather than going for the ASIC or SoC. So our IPs are deliverables for the FPGA as well. And software libraries for different applications, and working with the EDA tools companies to make it easy go for their design cycles. So this is our family overview. So the AR32Z is a scalar processor. AR32E is super scalar, and 128B is 128-bit vector processor. For AR32Z and AR32E, we have optional CMD or DSP core processor interface, and the applications are mainly similar, like sensor interface or edge computing, MPSoC for AI accelerators. Both of them are very low power compared to others commercial RISC processors. And the benefits of this core is that many of us is familiar with existing microcontrollers in the markets, for like M0 to M4. So we can deliver the similar performance in a single core, ranging from M0 to M4, and AR32E can give the similar performance like M7. This is the implementation results of AR32Z in FPGA. So we use RTX 700T device, and we run it at 100 megahertz. And here is the LUT slice counts. So when the AR32Z core itself, LUT slice count is very low, around 1,500. And we measured these dynamic powers using the Vivado. And Vivado gives us that the dynamic power for the core is around 7 milliwatts. So what we tried to the similar SoC using the microblades and measured the board level power. So when we run the similar SoC in the same board for the microblades based SoC and AR32Z based SoC, so we got the current number difference and measured in ammeter. And also from the Vivado results, we have found that our core is, even in FPGA, is 77% lower dynamic power than microblades. So then we then ASIC synthesis and PNR for TSMC 40 nanometer in using Dolphin 6 track library, and the clock frequency was 350 megahertz. So a standard cell was around 11,316, or maybe around 12,000. So the dynamic power was very low, even at 350 megahertz. It was around 6.9 microwatt per megahertz. This is the another feature of AR32Z is connecting the AI accelerators or coprocessors tightly coupled to the tightly coupled with AR32Z, in a sense that if we place these accelerators in the HB or AXI bus, usually it takes long latency. But we want to reduce the latency by tightly coupled with the AR32Z. And already AR32Z have a tightly coupled data memory interface. This tightly coupled data memory will work as a scratchpad memory for this accelerator. And there would be a data mover which can transfer the data from the MIPI sensors or DDRs. So as a result, this is making a triangle. That triangle triangle consists of your processors, tightly coupled data, and accelerators to deliver not only low power but also high performance. And in these configurations, we have our intelligent clock gating options, so which will give a low power solutions for the existing AI accelerators as well. This is our AirSim. This is the simulator I have mentioned before. So this is, for an example, lots of SoC. That's I think all of the SoC have a processors, bus, and peripherals. So what we did that when we conceptualize our design, we connect the different Verilog models or Verilog components together, license the IPs, and then simulate in the Verilog simulator, which takes a long process. But in ARSIM, what we are proposing that we are giving all the peripherals, all the buses, C++ models that you can connect according to your design requirements, according to what you are conceptualize, what you are thinking about, and then simulate the whole SoC. So for this reason, we have a AirSim C++ model library, which contains all our processors models, as well as bus models and common peripherals model. So you can just pick up and plug in. And these models are cycle-accurate models in contrast to RTL. And later on, we are planning, we are working to provide the features that even some customers may have their own blocks, customers block, which do not have the C++ model, but they have the RTL. So they will provide us the RTL. We will do the C++ conversion and connect it to the AirSim for the simulation. So this before doing the full SoC in RTL, so this enables you to test your firmware as well as start developing the firmware before the RTL is actually finished. Once you have verified that your requirements are sufficient for this SoC and simulation is well enough, then this AirSim will work as a verification engine, as a golden model for your later on for the RTL verifications. These C++ models are easily connected to the RTL simulators, and we are also right now working with some commercial idiot tools, for example, mentors, model sim, and Xilinx's Vivado synthesis simulation tools. So these will be connected to your RTL simulator, so you can verify your RTL as well. So this is the ASA processors. So we are here, AR32Z is done and AR32E is ongoing. And in this year, we are going to release the Zenon, which is an FPGA-based SoC product. And in the early next year, we are planning to release our 128B vector processors, and then 4 processor clusters. After that, since we will have the vector processors, we are planning to develop our own vision processors for the smart camera or security cameras, or maybe automotive. And then we are planning to develop the chiplet-based multi-core in end of 2022. So for the edge AI solutions, ASA have three different perspective to solve these issues. Like one is tightly coupled the custom accelerators with ASA processors. So benefit is low latency, low power, and also the complete FPGA solutions are available. And of course, another one is vector processor. So the benefits of vector processor is that you do not have to have license a custom accelerator, rather than you just write your acceleration functions in C, C++, or maybe in Python. And the multi-core is based on the chiplet. So for the suitable, this will be suitable for AI ML application, including 5G or maybe some GPU the applications that maybe GPU is not suitable for the power. These kinds of applications will help to achieve low power. So this is the Zenon that we are about, that FPGA evaluation board we are going to release in this year very soon. So it will initially support the free autos, and initial release will be single core, but next release will contain multiple processors, up to 4 processors initially, but maybe we can support up to 16 later on. And also there will be AI accelerators which will be tightly coupled with the cores. So any developers can not also the students can try to learn the RISC V ecosystems using this evaluation board. And since this is in FPGA, so they will be able to connect their own peripheral blocks into this SoC and try to build their own SoC. This is the ASA engagement objectives. We are actually looking for a strategic partner to accelerate ASA business success, but also we are want to contribute for the future development. So for the development purpose, we are looking for foundry support, packaging with emphasis on chiplet technology, accelerator developers. So we want to connect with third-party accelerator developers to tightly couple with our processor to bring them new solutions, and development tools and RTOS development.
Thank you very much. So now is time for questions. So please post question to the Slack. Okay, I have questions. So you developed the vector processor as a accelerator. So that means what kind of host processor connect to your accelerator?
Yeah, that's a good question. So yeah, if you want to use the vector processor as an accelerator, so you can choose any host processor, maybe host processor from ASA RISC V, or maybe other RISC V, or maybe even you can go for other ISA like ARM is also possible. It's okay. So we are independent of other host processors.
Thank you. And other question from audience: are there some benchmark demo for inferencing?
Yeah, we are right now working on the benchmarking. So yeah, benchmarking results will be available hopefully in the next exhibition somewhere.
So, what kind of benchmarking are you working on? For example,
Oh,
MLPerf or
yeah. Right now we are working on MLPerf and also some BLAS, basically in algebra solve on some programs, subprograms, basically matrix multiplications.
MLPerf 0.7?
Mm. As I mentioned, that we are working on it. So yeah, we still wondering. Of
Okay,
course, yeah, we welcome if you have any suggestions.
so to be announced soon.
Yes.
Yeah. Okay. Is there any question from audience? Okay, another question. Is upcoming vector future compliant to disk 5 vector spec?
Yes, RISC V vector specification 1.0.
Oh, okay. Is there any extension of the instruction to
We are
vector?
right now focused. Yeah, well, we are focusing on RISC V vector extension RVV 1.0. No custom extension, just the
Oh,
proposed
okay.
RISC V extension RVV 1.0.
Okay, thank you. Another question. So, do you already start business in Japan?
Yes, we already have office in Japan, and we are discussing with several customers, and some evaluation is ongoing.
Oh, that's great.
Thank you.
So, any question from audience? Okay, thank you very much.
Thank you.